Welcome to Maths with EJD. In this video, I'll be showing you the Python implementation of the Watts-Strogatz model, which is a representation of small world networks. Just like I said in the previous video, the key properties of the Watts-Strogatz model include high clustering coefficient, like regular lattices, short average path length, like random graphs, and then, of course, we have the balancing of local cohesion and global efficiency. So, I mean, a very good example of that is you have a group of very closely knit friends, but then you do not hesitate to reach out to unknown people when the time arises. That's a very good example of this. So here, as usual, we are using the inline one. We are importing the NetworkX library, which is basically used for networks and graphs in Python. And it is important. So you have an alias for it, which is NX. Then we have the matplotlib.py plot, which is for, the representation of the graph itself to show us the graph. And the parameters you require for a Watts-Strogatz model are the number of nodes, the nearest neighbors you want each node to be connected with, and the rewiring probability, which stands out what the Watts-Strogatz model. Okay, so currently we have 100 nodes and we have four nearest neighbors. That means each node is connected to these many nearest neighbors. And then you have the rewiring probability of 0.1, which is the probability of rewiring the edges. Okay. And then in line 10, we have the actual implementation of the Watts-Strogatz model. So it happens to be a module, or if you like, a function in the NetworkX library in Python, and it takes parameters, number of nodes, nearest neighbors, and rewiring probability. From lines 13 to 16, that's where you have all of that showing. So line 8, that's where you dimension the figure you want to use, and then nx.draw, that's how you get to draw the small world graph that you have declared in 10. Then the node size is 50. You can change that. With labels, you can make it true. This is false currently, then the title and all that. So if you just run this, see what you get. Okay, so we have something like this. Now, the issue is that, each time you run this, you are not guaranteed you get the same shape like you got now. So if I keep running it, you keep getting different shapes. Okay. So it keeps changing. But the fact remains that the number of nodes is 100, the nearest neighbors are 4, and then the rewiring probability is 0. So can we play with this a bit and see what happens? Can we tweak some of the parameters? For instance, let's start from a very simple level to probably see some kind of understanding. So what if we start with, I mean, this is a crazy one, but let me just say one, one makes no sense because it says k raised power n, k greater than n, choose smaller k or larger n. Okay, so you need a particular number of nodes for this to make sense. So this is still not making sense. So let's go to 3. So 3, of course, if you have three nearest neighbors, right? Four nearest neighbors, I don't know. So number of nodes is 4 here. Okay, so the minimum you can have. So if you're talking about four nearest neighbors, you should have at least four nodes too. So, and this one gives us a kind of complete graph. Okay. Yeah, a complete graph with four edges. So what if we make it 5? Then it's okay, that's still like a complete graph with 5 edges. So what if, because we must have four nearest neighbors. So for 6 now, okay, this is still looking like a complete graph. How about for 7? Okay, for 7. So 7, no, you can no longer guarantee complete graph, because if it is complete graph, you still have everything in place. Okay, let's do 8 now. See what 8 gives. Okay. Still not, this is not a complete graph anymore, because you can get all the four edges you need without having a complete graph. So let's see 9. 9 number of 9 nodes. Okay, something like this. What about 10? See 10. Okay. Imagine for 10. This is what you have. Then, I mean, let's take it to 20 from 10. 20. Okay. We have this. So that's pretty much looking like the same. What about 30? Okay, 30 is something like this. How about 40? 40. Okay, 40 looks like this. And let's do 50. We have this for 50. And let's say 60, right? Okay, let me go 100. Okay, we already have 100. Okay, let me go to 100. Let me go back to 100, right? And see, okay, this is still 100. Now, can we tweak nearest neighbors? If it's, if for instance, I say the nearest neighbors should be 10 for 100 nodes. Is that possible? Okay, I mean, we have something like this. So, the connectivity looks a bit more, okay, because we have changed the number of neighbors. What if I make it like, okay, let me go back to 4 is close to 5. 5 is close to 4. So this is still looking like when it is 4. Then we have seen 10. Can we go to 20 now? 20 nearest neighbors. Is that possible? Okay, that's like possible. So we can get something like this. It's getting more interesting. Okay. Then we have say, what if I say it's 30 now? So if I say it's 30. Okay, that's still like this. Let me do 50 then. 50 nearest neighbors. That means every node has to be connected to 50 other nodes. So it's giving us something this dense. How about if it is 60 nearest neighbors? Okay. So it's to be more like this. We can't have 100, or we can have 100, right? Let me just go straight to 100. The minimum we can have for 100 nodes is actually 100. So now this is, I think, this is now like what you have in Erdo's Range model, where the probability of connection or forming an edge is actually 1. So that's what this is. That's the kind of thing this one is doing now. So let's take it back to, okay, okay, let me just leave it there like this and then try out something else. I'll copy this out now. And then so I want to play with the rewiring probability and see what the impacts are. So let me make it 100 nodes and 10 nearest neighbors and tweak the probability, rewiring probability a bit. So see what we have here now. So we have this. So you'll discover that, because we know that for Watts-Strogatz, the clustering is high, right? So you have very dense areas like this, but they do not fail to reach out to other other concentrations. So it's more like you have a group of friends very close, but then they don't hesitate to reach out to other groups of friends. That's what the idea is, and that's why it's called the small world networks. So this is 0.1. What if we make it 0.2? The rewiring probability is now 0.2. Okay, it's getting denser. So let's move it to 0.3. Okay, so getting more, it's getting denser still. 0.4 still going, then 0.5, 0.5, we have this. Okay, 0.6. Okay, let me go all the way. 0.6, we have something like this. 0.7, 0.7. I'm going all the way to 1. Okay, getting denser still. 0.8, 0.8. This 0.9. Okay, so let me go all the way to 1. So 1 now, we have this. Okay, so the rewiring probability is increasing the connections too. But what increases the connection the most is nearest neighbors. And that's how far I want to go with this. In the next video, I'll be talking about the third type of model. I think it's called the free state networks or something like that. So we'll be talking about that, and I'll do a video after that to also demonstrate the Python presentation of that. That is the Albert Barabasi network model. Okay. So if you have not subscribed to this channel, be sure to do that right away. Hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know if you want me to solve a problem or teach a topic. Like and share so that more people can have access to all this great learning. Till I come your way again, keep networking. Bye.